So first things first, we're gonna have a pop quiz. I'm gonna read this to you and you're gonna tell me the word. Actually, no, don't tell me. Raise your hand if you think you know it, because I know there are people who know more than others and we want to not spill the beans for the new people. Okay, so Emily prepared these. So there's a term, the definition is a lack of signal in an MR image due to spin dephasing caused by magnetic field inhomogeneity. What is this called? Okay, go ahead.
Dropout.
Yep, signal dropout, and it shows up as like little holes in the image, or just dark spots in the image. Okay, next question. The process of filling in or estimating intermediate values based on surrounding data points. Raise your hand if you, the usual suspects. What is it? Yep. Well, this one's too easy. Actually, no, I'll ask it. This jargon for like defining a part of the brain that you're going to care more about based on some anatomical or functional criterion. Raise your hand if you know that term. Who's not raising their hands? Okay, what term is it? Yep. Name two types of structural data that were acquired for the NSD data set. Raise your hand if you can name two. Two types of structural MRI data. Boss.
I should say it.
Yes.
Anatomical and diffusion.
Maybe more specific.
What type of anatomical data?
T1.
T1, yeah. Bonus question, what does T1 actually mean?
T1 is it's a particular relaxation constant.
Yeah. I mean, we didn't get into details of MR physics, so that was a bonus question. But yeah, there's too much to cover.
But I did mention the relaxation constant.
Yeah, that's true. But what that actually means, we didn't have time to get into, but like in further detail. Okay, that's good enough. Okay. So I forgot. So we have these bonus lectures. They're on the Dropbox. I mean, we don't have time to get into them. From yesterday, there was this one. It's accessible. There's a Dropbox link on the syllabus if you just want to look at it and download it. Otherwise, they are on the IMAX. We don't have time to get into this, but if you're interested in ultra high res or sub-millimeter Fmri, there's a whole talk on this, and I'd be happy to chat with you like in the afternoon. But it's there. And for today, there are also bonus lectures. So I just want to alert you to that. In the afternoon, there was some of this happening, like random discussions, like on the whiteboard. So I think that's good. So random topics that you're interested in that you may not think everyone is interested, just chime in the afternoon, and we can do that. This morning, beware that breakout discussions are actually going to happen. So be ready. Lecture 6, for various reasons, has been moved at least to tomorrow. So that's the one supposedly on connectivity and stuff. Basically, there's a lot to cover in lecture 4 and 5, so that's the primary reason there. And so today is essentially as similarly structured as yesterday. Lectures and quasi-discussion in the morning, and we have 3 more example scripts that we're trying to get through in the afternoon. They are pretty hefty. The complexity is scaling exponentially. So we'll just go as fast as we can. Any questions? Oh, anything at all? Really? Nothing? Okay. So yesterday we talked about logistics and things specific to NSD and got a whirlwind tour of Fmri and the type of data you get from that. Today we're getting to analysis and like what can you do with the data and things of that nature. Oh, good call. I have a clicker. I put new batteries in. I believe this should be good to go. Click, click, click. Okay, so I guess historically, Fmri has gone through various trends and people get excited about certain things. And I guess my general view on all of this is they're all just different ways of characterizing the data we acquire, right? And so I guess I emphasize the similarities as opposed to differences. And so today we're going to go over 4 approaches, I guess, and then connectivity was supposed to be yet another one. And of course, there's more than that, but these are kind of the dominant ones. And so I'm trying to give some sort of overview of this, as well as my personal take as to what they are and how they are different and similar, and limitations or good things about them. So that's kind of the overview. So the simplest thing, and I put this in quotes because I'm sure you've heard it and it's kind of a snarky term, is like, what do you do with fMRI data? You have different conditions that you put your subjects in, and then you essentially go find regions that actually are selectively activated by one over other. Or in other words, you essentially are subtracting activity. Find regions that respond more strongly in condition A than condition B, right? This is 20 years old, 30 years old. It's like maybe the first thing you might do with this imaging technique. And I'm just stealing this figure from a textbook. I mean, you see figures like this all the time. Briefly, this is a structural image underneath, and it looks quite bad, but it's okay. It's a structural image in grayscale underneath, and then after you acquire some functional images in time series and do some analysis, it's showing in a heat map regions that, and in this particular experiment, these are p-values, and we'll go a little more detail in a second, but essentially these are putative regions that are showing statistically significant increased activity to some task condition or stimulus condition compared to another, right? And so this is bread and butter, old school blobology. So now we have blobs in the brain, and I guess what I want to say about this, and we'll go into some more detail in a second, so that's what I was just saying. You're essentially just subtracting 2 numbers and seeing if that difference is statistically significant. And my view is certainly, we poo-poo this, and it has limitations, but there's nothing sort of intrinsically wrong. There's nothing invalid about this type of very simple analysis. And what I'm going to do on the next couple slides is go through a number of bread and butter statistical issues or analysis issues that come along as soon as you even do this type of simple approach. So I know some of this will be review, but everyone needs a review of these, I think, basic concepts. NHST, null hypothesis significance testing. Of course, we could talk about Bayesian statistics and whatever, but again, I don't think there's anything wrong with p-values. It's just what we do with them and and how much emphasis we put on them. So, 1 slide review of basic statistics. And this is related to blobology. I mean, just the connection, just to make it super clear. I mean, we were looking at p-values on that previous figure. We were using a color map to represent p-values, which you can think of as statistical evidence for rejecting the null hypothesis. So let me unpack some of those terms. Null hypothesis, let's just use everyone's favorite example. Let's say we measure responses to faces and houses. The null hypothesis is any given brain voxel or region really doesn't show any difference in activity across those 2 stimulus conditions, let's say. So that's our null hypothesis, that A is equal to B, essentially. The response to A is equal to the response to B. Great. So I'm just unpacking the jargon here. So what's significance? I guess we don't have time to go through all the statistics, but basically, under the assumptions of that the null is true, given the data, how unlikely is that? How unlikely is the data given under the null hypothesis? So again, we define our null as the response being equal across the 2 conditions. And then finally, the term testing is, we're kind of like testing, is it true or not true? We're kind of making a choice. Either you reject the null or you accept the null. And that, of course, is arbitrary. P less than 0.05 is the traditional cutoff that you decide yes or no, right? So this is all kind of review, but important. And properly thinking about the meaning of what a p-value is really important. Again, it's the probability of some observed data under the null hypothesis. And so if that probability is really small, we are more likely to reject that null. In other words, accept or believe the fact that the response to the face is higher than the response to a house. Right? Okay. Maybe I should stand over here. So you may hear other jargon, statistical inference. That's just a fancy term for essentially constructing these p-values and using them to interpret your data. And other basic jargon and terminology, type 1 error. So there is no effect, but you think there is. So like you draw a little hotspot even though there's not actually an effect there. That's very common, and it's also termed false positive. Like you have a positive result, but it's actually not true. And there's also, of course, type 2 error. Maybe I should use the other thing if you have it. Type 2 error is there is some difference in response. Like A was actually greater than B in reality, but maybe you got unlucky in the trials that you measured, or you didn't get enough data or whatever. So there is an effect, but you failed to detect it. In other words, you don't draw your little blob there. And in signal detection theory terms, you can call that a miss. Okay, one last thing that goes very closely with type 2 error is power. So again, the effect is there. How likely are you going to detect it for a fixed amount of data? So these are all kind of basic statistics 101. Is this on? Ah. What happened? I'll just stand here. This was working. Okay, and then one last thing is this, let's just step through it. It's very basic, but it will take a few seconds just to wrap your head around it. Right, the 2x2 table. This is H0 is the symbol for the null hypothesis. So this is the case that the null hypothesis is true. In other words, there is no effect. This is the case of the null hypothesis not being true. And then the rows are what you do after you do your statistical test. So this is reject the null, so believe that there is an effect. And this is accept the null, which is just like, it doesn't look like there's an effect, right? And so we can kind of go through each of these squares. Easiest case is this. The null is not true. There is an effect there, and you reject it. So you call that like a hit. That's good. And then let's just go down. There is an effect, but you're accepting the null. So your thing didn't reach significance. So you're going to say, I didn't find that effect. So that's a type 2 error. There was an effect, but you didn't find it. And then the null is true. So there's nothing going on. The response is exactly the same across two conditions. And let's say you say that there's effect. So that's a type 1 error, false positive. And then the other case is there's no effect, and you correctly don't color it in the blob. So that's a correct rejection. Anyway, so this is very basic statistics, and it already is important to think about, you know, again, in the context of subtraction flavor analyses. Okay, there will be a breakout, and so that's a nice opportunity to discuss or ask questions, but I want to also go fast, but also slow down. So we'll be there in a second. Okay, so one thing I think is important to keep in mind, and this is kind of basic statistics, is effect size. So just thinking about p-values, quantifying p-values tells you nothing about effect size. So my definition of effect size, and it's kind of, there are different definitions out there, is kind of the magnitude of some phenomena. Some, in the case of Fmri, it would be like the amount of extra activity to some stimulus condition or experimental condition from here to another. And importantly, this, if you think about effect sizes, they do not change with the amount of data that you collect. So let's talk about some examples here. So examples of effect size measures are, say, correlation coefficient. So think about a scatter plot, and you're measuring two attributes from different subjects or different voxels or trials, it doesn't matter, and you find a correlation of, say, 0.5. Let's say those dots were trials, and you collect 10 times as many trials. The strength of that correlation, say 0.5, is theoretically stable. Like, it doesn't matter if you collect a billion trials, you're still going to get, hopefully, a stable measure of that strength of relationship, 0.5. Another example is regression coefficients. So we talked very briefly about GLMs. So you do a GLM, typically an Fmri, to estimate the amplitude of the evoked response to different conditions using the predictors, if you remember that. And again, in that scenario, if the beta weights are, say, in units of % signal change, even if you collect 100 runs, you should just converge theoretically on having, deducing that the response to stimulus A is like 2%. Like 2 is not going to grow with more data. One last example, just differences as means. Again, my response to faces is like 2%, my response to houses is 3%, so that's like a 50% effect. Even if I collect more data, that should stay stable. And Again, this is in contrast to p-values because, of course, if I collect more data, I'm going to get even more statistically significant effects. Like p will infinitesimally go towards 0. And again, we'll see a more concrete example of that on the next slide. But at the conceptual level, hopefully this is clear. Yeah, so they just beat this concept like a dead horse. P-values are going to be contingent on how much data you collect or how many subjects you get, depending on how you set it up, right? You can quantify across subjects or across trials. And so you will often hear like, your effect is statistically significant, but it's tiny. And so that's, again, juxtaposing the p-value is not the same at all to the size of the effect size. So let's, and then one last gripe about p-values is, I mean, in the end, we all have to make some choice. Like either you believe the result or you don't. And so that dichotomy is a bit arbitrary and artificial. Okay, so I'm gonna skip over that. You can just read that, but let's go through the very simple example. Okay, so let me just walk you through this. Again, it's like a 2x2, so let's just focus on one case. All I'm doing is a very simple simulation, which I did, I mean, we could talk about statistics and code it up. It's very easy. But here we have let's say two conditions, faces, houses, or A and B. And the dots are just data points. I drew these randomly with some, Gaussian distribution, whatever. And the black bar is just the mean, and the red bar is the plus or minus 1 standard error. Like, again, bread and butter statistics. And similarly, I did that for B. And this first quadrant, let's talk about the 2x2 design here. This is the case that there's no effect. In fact, the mean from which A and B were drawn was exactly 1. That's what I did in the simulation. So there's no effect. A and B are identical. That's no effect. And then in this case, we have a low amount of data, meaning we only have like 8 or 10 data points. All right. So that's what this is showing. It's one kind of experimental simulation. We go to the column side here to the right. There is an effect. So the mean is 1 here. The mean for B is 3. Okay. So there is a true effect going on. Of course, we have limited samples, so it may be hard to detect it. So that's the column. And then the row is the amount of data we collect. So clearly there's hundreds of data points down in the second row. All right. Okay, so hopefully that's clear what's getting plotted. So what can we say about this? Well, in both of these cases, I guess I didn't actually calculate what the p-value is, but this is probably not going to be a significant p-value. I mean, look at the error bars. This is like 0.5 or something p-value. And then like similarly down here, even though we've collected a lot more data, this is also going to be insignificant. And that's good, right? Because this was the case of simulating no actual effect, no difference between A and B, right? So we're happy. Okay, let's look on this side. This is going to be significant for sure. I'm just looking at the error bars. That's highly statistically significant. And also this will be even more highly statistically significant, right? The error bars are tiny. Now the key point is the p-value got shrunk drastically going from here to here, but the effect size didn't really change. Of course, the effect size itself, it has to be estimated. So if you calculate it, it's going to be different, but that's just because it's estimated. But because I told you what I simulated in terms of ground truth, in both cases, this was a 1-3 effect, right? So even though you collected tons more data, the underlying effect, which presumably we actually care about, the neural response or the bold response tripled, that didn't change across these two scenarios, even though the p-value shrunk dramatically. Okay? So I think that's important. And if you do Fmri and you focus on p-values, you kind of lose sight of the effect size, for example. So that's how it's relevant. Breakout. So find triplets and discuss the slides you just saw. Come up with a question or a comment. Go. Triplets. It can be even a story, like, oh, I heard this one case where whatever happened, and you can tell us a story. Hey, you can't leave. No, I'm kidding. Yeah, I have coffee. The way this is going to work is I'm going to call on 2 groups, and then I'll see if any other groups wants to chime in. Otherwise, we'll move on. Okay, group in the back. Tell us something that you guys discussed.
Well, I was just saying that it's probably very naive, but as when I've consumed fMRI data before, I've looked at pictures of brains, and there's always a big always interpreted that as meaning this is where the effect is largest, but it sounds like that's not a really a valid interpretation. It could be that that's where it's most significant.
Yeah, that's very interesting. And I have similar gripes. So if the signal strength, like bold response, and noise magnitude are homogeneous across space or across voxels, then what you just said would not be true. Like, take it at face value. But if the noise for whatever reason, if you're near a blood vessel or whatever, happens to be larger on the outskirts of your island, then certainly the effect size could be huge there. It just looks noisier, therefore the p-value doesn't seem, yeah. So that is definitely a potential issue in fMRI data. One more group, this group.
One thing we just kind of talked about more generally in stats is just how the criteria you use is like semi-arbitrary, and like the various ways you can manipulate statistics to try and get out a result that isn't really there.
You mean like the alpha value, the 0.05 thing?
Yeah.
Yeah, there's that issue. There's also, and it's kind of a mess, there are different statistical tests, like sign tests or rank sum tests or Kolmogorov, Smirnov, I can't say that. There are various, ways to get your p-value, and then you p-hack when you like choose the one that's smallest, right? So yeah, that's definitely an issue. Okay, any group wants to contribute? I like these, but we can also move. Yep.
So the figure, the fMRI figure you showed, right? So there's no indication of effect size there. So one of the implications is that maybe when you make your figures, if you're doing something like this, you're better off showing the significant voxels or significant clusters, but then actually your color bar should be some indication of effect size.
Yep.
Instead of
the And what we like to do is do two figures, or I routinely plot two figures. So you can plot something like, so again, faces and houses, you can calculate percentage larger than, so like how much percent larger is the face response in the house, and that's a number. So you can kind of plot that. It'll look noisy. That's the major downfall of this type of thing. And you can also plot statistical metrics like p-values or the t-value. Yeah, so I think, and then you suggested combine both, but I mean, it's a trade-off. You either get full information and have to look at two things, or get reduced information and look at one thing. But yeah, I think that's a good tool to have in your arsenal. Any other group have want to contribute, or we can move on? Yep.
So if you have a small effect size, what does it mean? Like, is it meaningless, or does it mean that?
Yeah, small effect size. Well, I mean, that you got to put on your neuroscience hat. So if you're measuring from one neuron and it spikes on average one more spike per second on a baseline of like 100 spikes per second, like the question is, does that matter to how the brain works? And I don't know, it depends on your theory of the brain, but it's no longer a statistical concern. It's like a how the brain works concern.
Yeah, but the fMRI is not direct measure.
Mm-hmm. Right. Well, fMRI being noise, I think that's a different issue. So, okay, let's just flip the example to fMRI. Let's say you find one voxel in the brain, and you're 100% sure it is significant. It's not like a random speckle that happens to be. Let's say it is, but like only 1 cube millimeter of the entire brain preferentially activates to whatever you're studying. You're asking like, and let's say it activates like 10% more only compared to something else. Like, is that important? Again, it just depends on your theory of the brain. It's not like a statistical issue anymore. Yeah.
On the same question, right? So thinking about effect size is highly dependent on your theory or your assumptions about what it's to say, right? But MRI data is, I mean, it's hard to make a connection with that with like cognitive theories, right? In the sense of, can I actually predict, for instance? Can I do cognitive neuroscience theories actually predict effect sizes on fMRI data? Or on something else, right? I think that's...
Yeah, I mean, if you fundamentally care most about behavior, then you could translate it to the behavior. Like, how much variance of reaction times do you think is important to predict? Or how much D prime individual differences are you able to predict given brain measures? So but then you have the same question, like if you can predict 1% more reaction time variance, is that important?
Right. So the question really is, I understand the general question, but the question about what exists in the literature, right? So there are behavioral theories that make very precise predictions about effect size that expect to find different conditions. Does the same thing exist in fMRI? Right? Because if there, and I would say that in most neuroimaging, I don't think that that's the case. And we have the ability to say, like, I would expect to have, like, I don't know, a very large effect size in this condition and a very small effect size.
Does it exist? I'm not the gatekeeper of neuroscience. Largely no, but yeah, I mean, in the visual modeling world, if you really believe your model and makes quantitative predictions, then that is a prediction of all the effect sizes. Like you expect this level of response to this type of stimulus and you increase the contrast, you expect this, you show a different type of stimulus, you predict that those are effect sizes because those are quantitative predictions. As opposed to, I predict higher activity. I don't know how much higher, but higher, that's qualitative. Cool, any other?
This isn't really what we discussed here, but I was just wondering whether you thought some opinions on sort of problems of subtraction. So I know it's like dangerous territory, but like Coffiston has like said this for a long time about how subtraction has the implicit assumption that the two cognitive processes that you are subtracting don't interact.
Yeah, that has a term.
So when you see faces, you're assuming that your brain activity is only one of the object plus face, as to any other things that might.
Yeah, for sure. That has a name. It was like pure insertion, or the problem of pure insertion, I think someone has called it. Maybe even Mark Desposito. But yeah, I have nothing more to add. Yeah, certainly the fact that you find more activity with that, what that really means in terms of the complex cognitive processes happening in your brain might be complex to suss out. Okay, I think that was good, so let's continue. Okay, as I mentioned, there are other issues. We're talking about subtraction, and then immediate issues come to mind, very standard ones in Fmri, spatial smoothing. Again, I'm just taking this figure from that textbook. So what the experiment was doesn't matter. It's the same idea, some structural underlay, some showing of p-values colored with a color map. And on the left is, let's say, the raw result. You don't do any extra smoothing. And then let's say on the right, what you do is first smooth the data. So let's briefly, I don't even think we defined that, but spatial smoothing means you essentially take a voxel and take some of its neighbors and average them together. And then you do that everywhere. So you convolve it with like a Gaussian kernel in technical terms. And let's say you do that to the pre-processed time series data and then run your GLM and find p-values and all that stuff. And let's say that's what the right-hand side is, and then, lo and behold, it looks qualitatively different. The center of mass seems a little bit displaced. One of these clusters disappears, as you can see on the right-hand side. And it is just a fact of life. I mean, there's nothing is invalid here. And the motivation of smoothing, just to make it clear, is Fmri is noisy. And so random uncorrelated noise will tend to average out when you average multiple voxels together. So if you flip a coin, that's not a good analogy, but random noise that might be up or might be down from voxel to voxel, if you start averaging voxels together, that will tend to cancel out. So that's the motivation, and that's good, except that when you smooth, you're smoothing the underlying signal also, right? And so what's happening is this hotspot here, even though it's a yellow pixel placed right there, it actually represents a footprint on the brain, right? You've smoothed nearby voxels into it. So yellow being here, this location, doesn't actually mean that location. It means these locations around it. But of course, if you just plot this figure, it's a little misleading unless you know what the heck has been going on. Anyway, so there's people know this, but just something to remind you about. And then one other just kind of statistical or analysis issue is like group level issues immediately become important. Maybe this goes historically with subtraction analyses because people generally wanted to do group analyses only back then. And so one distinction I think is important is kind of two different group related analyses. One is like the straightforward one, like you have 10 subjects and you're going to quantify your effect to make sure that it's significant at the group level. So on average, if you were to sample more humans beyond the 10 that you did in your study, do you actually find increased activity at that spot? So that's pretty straightforward. But of course, some people want to do group differences. So sample healthy young adults and sample some patient population or whatever group level differences. And now you have two groups. And now you want to establish whether one group shows increased activity in, say, some condition compared to the other group. And so if you do that type of analysis, there are things to watch out for. So this kind of relates to the Fmri talks from yesterday. There are a lot of things going on in Fmri, sources of noise, and if there's something that systematically co-varies across your two groups, you're gonna have some issues. So if your kids move more and you're comparing them to adults, they're gonna have noisier data. So your p-values are gonna be not as great than the adults, and then like all sorts of things can happen. So I just wanna kind of alert you to that. Okay, and this now brings up issues, hopefully you remember from yesterday, to dump 10 people in the same pot, you have to like somehow compare them. So this is a spatial issue, right? So the MNI and FS average become important. So just to remind you, these are two different humans. This is real size in a sense, and look how vastly different their brains are in just in terms of size, let alone the soul side gyri. And conventionally or historically, people use volume-based approaches, so use stretching and scaling, or even some nonlinear warping. MNI is what we talked about, Talerac is a different space. And just to remind you, there are other ideas. If you're focused on cortex, then you can actually trace out the surface and then nonlinearly warp these surfaces together, which theoretically is more accurate. And then, of course, there are other approaches like actually find a real brain area in each subject, and you don't actually have to warp them to each other. You just know that something is something. So like V1 is V1 is V1. I know I have to match the size of my V1 to your V1. We can just maybe use some anatomical or functional criteria to find it, and then we're good to go. So again, these are just issues that immediately arise once, even if you do the simplest possible analysis of, activity is higher in one condition than another. Okay, so just to summarize that approach we did it in like 10 minutes. Here's kind of my take on it. Like in a nutshell, what is this? Well, we're trying to keep it simple. So it's essentially just determining whether the bold response is higher in some experimental condition of interest than another. I mean, that's it. And I think there's nothing wrong with this approach. I mean, just as long as you understand that what it's predicated on, and of course, statistical assumptions and all that. And just to recap, and then there's all these interesting issues that come along for the ride that you have to think about even to do that type of analysis. Breakout. This can be short if that was not super interesting, but let's take 2 or 3 minutes just to get in your triplets. I'm gonna call in this group. Hey, hello. Okay, this group.
So we talked a little bit about effect size and the relationship with just noise and how noise could affect that, and how if it's difficult to parse out whether you have noise or signal, even if you're using things like spatial smoothing and that could just affect effect size.
Yeah, that's an important issue. Yeah, it kind of depends on the specific effect size measure, how noise interacts with it. But this is a good excuse to do simulations. If the effect size is simple, like the differences of two means, like A minus B, then random Gaussian noise applied to A and to B, it's pretty innocuous. Like, yeah, noise will cause it to go down or up, but on average, there are formal statistical terms for this, like your estimator's consistent, whatever. But that's easy. But others, effect size measures might behave more weirdly. Correlation, you add noise to a two-dimensional scatter plot, it's not unbiased. You will go towards 0. So now you have this weird bias. The more noisy your fMRI data is, or your behavioral data, whatever, you tend to get 0, as opposed to staying at the proper effect size. One more group who hasn't gone. Who didn't I? In the back? I guess you volunteered, but it doesn't matter. You guys go. Oh, okay.
But they're within the same vein, things like effect sizes. Once you determine them, how do you determine they're meaningful, and how do you predict ahead of time whether such an effect is even relevant to you and your theories of not only the brain, but also because we care about language, are they relevant to theories of linguistics, and how do you relate two domains as you try to interpret your data?
Yeah, I guess the first thing that comes to mind is related to some more concrete thing like behavioral outcomes.
Yeah.
Any group want to contribute, or should we move on? Yep.
What I think that it's hard to estimate how much should we use, how much should be the area of smoothing, how much should we go for such type of reducing the noise, and maybe the proper approach is to go for it and to understand whether we can interpret what we obtained, or whether we should reduce the noise more, and only by understanding if it's if we can interpret the result, or whether we should reduce noise even more, we can estimate exactly this level of smoothing, which will be the proper one. Otherwise, what would you recommend? To what extent should we use this tool? What should be the judgment criteria? Is it enough or not?
Yeah, it's a hard issue. I mean, the most honest approach is show the result at various levels of smoothing, because if we don't have any priors on what to use, you don't want to only report the one that looks good or that you find interpretable.
Yeah, that looks good. That's exactly what you can justify.
Yeah, and another general idea out there, and I'm just parroting, typically you want to smooth to the scale that you think exists. Like we try to measure activity patterns, right? You do fMRI, you get complicated activity patterns, and maybe you're interested in contrasting two, so A minus B. That is a spatial map of something. Like it's in volume, it's on the surface, whatever. And that has a spatial scale. Like it's either a really low frequency thing, or it's a really punctate thing. If you have a prior in what you think it should be, or if you know what the right answer is, then matched filter theorem says you smooth large enough to match that scale, and then that is optimal. And that's ideal but that never really happens because we don't really know what the answer is. Otherwise, why do we acquire data? So I don't think there's an easy solution to that. Cool. Okay, so that was subtraction. So then we turn to MVPA. I don't like the term MVPA, but what I mean by it, I'm using it because people use it. It's like this convention thing. But what I mean specifically by it is just bread and butter MVPA, train a classifier, decode what the stimulus is, or the experiment, right? And this historically came, a little bit later after subtraction. So I'm just gonna give you the kind of two slide overview of what it is and just get everyone on the same page. Again, bread and butter, you use a classifier. So in statistics, all that is if you know regression versus classification, regression is use a bunch of variables to predict another variable, which is continuous. Classification is use a bunch of variables to predict a variable that happens to be discrete. That's all it is, right? And so it's the use of a statistical classifier to distinguish between experimental conditions based on brain activity. Okay, so let's just unpack that. I'm just stealing this figure from this review from a while ago now. Let's just walk through it. These are our voxels. So we have a bunch of voxels that we've chosen somehow. Not important how we do that yet. And we have like discrete trials. So let's say we've done GLM analysis to extract trial-wise amplitudes or something. So you get a bunch of data, and each of them had an associated label. mean, there was an experiment. So this was the stimulus that was on the screen or whatever you had the subjects do, right? So we have a bunch of data. So this is trials by voxels and this is trials by one. Okay, great. So we have some training data. We're gonna fit our model, our classifier, right? And we do some fitting, symbolize that with a little box. And then we go to some new data. Looks the same, right? A bunch of voxels, they have activity. This could be different trials or even different subjects, depending on how you wanna set it up. And then you ask, given this new set of data, push it through your classifier, it's gonna make a prediction. It's gonna predict the output variable. And then you get an answer. And then you just check, was it actually what happened in the experiment, right? Super simple. You don't have to make it more complicated than that. And that's the setup. So you wanna find effects so you're happy when this thing actually matches that thing. And you typically quantify that in % correct. Should ring a bell. So you will hear things like, oh, we found that patterns of activity in this region can be used to successfully predict which of, say, 2 of the experimental conditions actually occurred. And you might get like 70% accuracy, right? This is all like standard nomenclature. A couple of properties of this approach that I would just want to mention. And again, people know this and I'm just reviewing. It's multivariate, and that's referring to essentially how many brain units are you using in the analysis, right? So I'm going to remind you some little mathematical jargon. Of course, we could teach linear algebra in a week, but we're basically using many voxels, as we just saw in the diagram. We have a whole row of them, so 100 voxels, let's say, and we're going to estimate weights. So we're computing a dot product. We're doing a weighted sum of voxel activity. And then we need a function to squash it or basically map this continuous output into binary outcomes like a logistic function. So it's f of this dot product is going to predict some outcome, right? So, and the key point is there's lots of voxels. So we have lots of weights getting adjusted on this pattern of activity in some part of the brain. So it's multivariate in that sense, in contrast to a t-test on one voxel, which was subtraction, right? That's one voxel at a time. So the fact that it's multivariate, most people find it interesting because you get more statistical power. So if you have tiny differences between your 2 conditions and one voxel and then a little bit of difference in the next voxel, you know, you do t-tests at every single voxel, it might be not significant, but if you are able to cobble together a bunch of weakly distinguishing voxels, you may find, you know, successful classification performance. Right? So this was kind of the motivation, or one of the motivations of this approach. Another aspect is, if you think about it, the directionality of this model is flipped. So a t-test, you can think of, you change the experimental conditions and you're looking at the effect on the response. Whereas here, as we saw in the diagram, you're kind of you start with activity and then you're kind of predicting the experimental conditions. So the directionality is kind of reversed here. Another aspect of this is, and we already saw it in passing, we start using jargon like training and test. And this is very machine learning-y. And so now you're in the world of machine learning, you have to think about separating your data and then resampling and all this extra kind of machinery. So that kind of comes along. and of course you can get arbitrarily sophisticated with your machine learning stuff. And maybe we'll get into some of this on tomorrow or the next day, I forget. Support vector machines is fancy technique, although it's now classic. It's probably 20 years old. That's like a fancy machine learning method, but of course there are simpler ways to classify data, like nearest prototype, which is essentially for the 2 conditions, average across all the trials, and then for some new data that comes in, find the closest one in a voxel-wise sense. Anyway, so that's like a very simple classifier, but you can use more complicated techniques, of course. And certainly performance may be much better if you use more powerful or better regularized techniques. Okay, so this is all kind of review. And a couple more points about MBPA. So it's often said in literature, you know, that, oh, now we're sensitive to fine scale activity patterns. And what that means, just think, I don't have to draw a picture, but like, again, you have a slice or a surface and you might see, you know, differences in tuning on very nearby voxels, and that's fine scale, as opposed to a generally blob-like structure. so it's possible that it is the case that if you use this approach as opposed to a, smooth the data and do a t-test, it could be that MVPA is sensitive to fine scale, but it's not guaranteed to be the case. Like you can have a blob effect and MVPA can also find it, right? So just the fact that it worked doesn't mean that you're now, decoding fine scale activity from your data set. You have to do you have to show that. And another weird thing about MVPA, or at least I find this weird and interesting, is it abstracts away from the data. And this is not necessarily a good or bad thing. So what that means is, if you do the standard thing of you put down your searchlight, which is actually the next concept, but you do some MVPA, you get % correct, and then you do that in all your subjects. Now you're making, you're reasoning about this new entity, % correct. And that's an abstraction because you're no longer talking about what is the bold response to experimental condition A or experimental condition B. That's like a number, like 3%, 4%. You're now talking about this % correct thing. And that's an abstraction that kind of hides the actual activity, the actual bold response. And you could argue that's good because maybe the fine scale pattern is actually different in everyone and you don't actually care about that from a neuroscience point of view and you just care about some kind of second order characterization of the phenomena. So you could argue it's good. You can also argue it's bad. Actually, maybe we should stay close to the data and actually think about patterns of activity in the brain. So that kind of is implicit in this sort of approach, this kind of % correct stuff. Okay, and I did already had to use this term searchlight, and I mention it here because it just kind of comes with MVPA. So let me just briefly describe what that is. We have a large brain volume, and essentially how do you decide which voxels to put into this kind of classification paradigm? I mean, you could dump all the voxels in, but essentially you're heavily overfit, and this is going to be challenging to get good results. What that actually means, let's not get into yet. But a different approach is you kind of have little groups of voxels. So just select little subsets of the volume. So you like move around and select a 5 by 5 by 5 region or something, and then dump those 125 voxels into a classifier and then try it out. So that's the idea. And people do this all the time. You can also do it on the surface, like go along your cortical surface and pull out little circles or something of voxels or vertices to use. So that's just a term that you should know. And you can think of this as it's voxel selection. And actually, it's interesting. Imagine dumping all the voxels into one gigantic classifier. If you set the majority of those voxels to 0 weight, and then some of the weights are non-zero, I mean, that's effectively equivalent to a searchlight. So really, the searchlight is a way to regularize the weight estimation. And it's important because you don't have a lot of data. You can't realistically estimate 100,000 weights on the voxels for only 100 trials of data or something, right? So it makes sense to want to do this, but you can kind of think of it as essentially just another way to select which voxels to put weights on. Okay, and that was just the point I was explaining. Okay, breakout on those topics. So try to discuss what we just talked about, MVPA and machine learning and stuff like that. We'll do this for 4 minutes. So what's your guys' team name? Ainsley. Oh, all right, Ainsley's team. What are you guys discussing or a question? Or?
We had a question for you, which was about in terms of localization with MVPA. There's potentially 2 approaches you could take. Where one would be a searchlight approach, like we talked about, where you're doing subsets and accuracy map. The other way would be to do a whole brain classification and to look at the weights on the boxes. Let's assume you have just a ton of data. Do you have any thoughts on pros and cons of interpreting voxel weights when it comes to certain classification? We want to know which area is formative for classification.
I mean, there's a paper on this. I'm sure you read it, the Hoffa paper. Actually, mention it on one slide. It's again one of these issues. There's no good answer. I mean, the whole brain thing is nice because you don't have to make a choice, and in theory it will work, but it will fail because you don't have enough data, and so you'll get either random looking weights that result because you just didn't have enough data to put estimates on all the voxels. So that's the downfall of that approach. So for that reason, because Fmri is noisy and you get limited data, I would be inclined to want to do the searchlight method to localize.
What about weights within an ROI? Like, how interpretable do you? I've sort of heard mixed things about the ability to interpret what classifier weights.
We need to be more specific. So you find a weight on you do a searchlight in the little circle of voxels, great. And then you find one voxel seems to have a high weight. So what is the proposed interpretation you want to make?
Well, I guess it would be you start with an ROI, like a visual cortex, right? And then you run your classifier, and then you look there to see if you say these voxels have the highest. I guess it depends on your classifier, but absolute value of weights is highest in these in this region subset of visual cortex.
Yeah, I should reread that paper, but off the top of my head, ironically, in order to be more confident of interpreting the weight to figure out which of the 1,000 voxels to actually has information, it kind of brings you back to univariate approaches. So like, out of these 1,000 voxels, you see some hot weights in this part. Well, how do you really know? Well, why not just go look at that one voxel and look at its response under A and under B, right? So you're kind of back at doing a simple t-test or effect size quantification of the thing, which then raises the question, like, why do the classifier in the first place? Like, why not just...
Because if you have neighboring voxels that have the opposite, like they respond in the opposite direction, but to a large degree,
right.
Then the univariate approach isn't going to really help you.
Well, it could. I mean, only if you smooth, then you're going to smooth out the signal.
Yeah.
But if you don't smooth, then theoretically, again, with enough data, you will see speckles of actual tuning, right? This voxel loves stimulus A, and this next nearby voxel hates stimulus A. I mean, you could theoretically get that just from doing univariate. It's just that data are freaking noisy, so then, right, we play this game, we go around in circles.
So I understand that if you try to go whole brain analysis first, there's the problem of way too predictive amount of data you have. But there are ways in which you can do with this, like the regularization techniques, like you will see regression or Gaussian square regression or ridge regression, or kind of those things. Does that solve the problem?
Yeah, I hesitate to use the word solve, but certainly we have these principled and statistical techniques that help address the problem. But, you know, there's no free lunch, you know that saying? Like, yeah, if you don't regularize at all, you're screwed. But we have regularization at our disposal, so it can help, and you can start pulling something out of it. But you're still fundamentally data limited, right? So it's not like a full solution. And the best way to do this is simulations. Like simulate 100,000 voxels, put it in effect, generate an hour of data, and see how well the weight map looks compared to what you know to be the case. But you know, realistic Fmri data is also really hard because very structured noise and very structured cyclic. But yep.
So for NPL classification analysis, it doesn't necessarily need to be searchlight or looking at the brain and that also because we can still use the ROI approach to have a hypothesis about this region of the brain should show differences between these conditions. And so instead of using subtraction and variate analysis, I want to see how the different regions and conditions are different between our. And I have hypothesis about that. I just it's my analysis.
Yeah, but are you drawing the distinction? Like Kartik was saying, like the use of MPA to try to localize where the effect might be coming from. Are you saying if you're happy to just leave it at it's somewhere in the ROI, you can use MVPA and that's fine, and not worry about interpreting weights? Yeah, that's certainly fine. Any other group want to pipe up? Yep.
We discussed about
Oh wait, what's your team name?
Sam named it the mongooses.
What? Mongooses. Mongoose. All right, you guys are the mongoose. What you have a comment, question?
we discussed about like if you get different results when you conduct a univariate, that's the subtraction, and the multivariate analysis, how to interpret that. I think it makes sense like if you got non-significant results from the univariate, or you got significant results from the ambiguous, probably because the ambiguity has more power. It makes sense. But what if like, you got significant results from the univariate analysis, but non-significant results from the multivariate analysis? How to interpret that?
I do think it's possible that can hurt. Let's say you use a horrible classifier or you mess up something. So I think it's possible that it might happen. I don't know. My view on that is I don't see and this kind of goes back to how I think about all these things in the first place. You're all like, it's the same data set. So it's just that it's our fault for thinking that there's a confusion. Like the data are the data. And because you used a crappy classifier, you didn't get a significant thing, but it's your fault, not the data's fault, or something like that. I'm not sure I don't know if people have opinions on this. Another way to think about it is if you seem to have confusion from a given set of data and your two analyses are suggesting two different things, you might think about writing down the two hypotheses or models or whatever you want to call it of what the data are like, and then like get more data to kind of distinguish the two. So you're kind of shoving the burden on a new data set to kind of clarify your confusion with the first data set.
It's like I was thinking like for the univariate analysis, it's probably more like we gave the same weights to all the voxels in that region.
Oh yeah. Oh, so that's a good parallel. So if you take an ROI and smooth all of those vertices together by averaging all of them, that's equivalent to putting a weight of 1 on all the voxels, right? When you average a set of numbers, it's equivalent to taking the dot product with a vector that's all 1s and then normalizing.
So in this case, it's more like that you have the aggregate to giving weight of 1 to all the voxels. Like if we use different algorithm to do the MVPA, because the algorithm they didn't find a way to give others weight to all the.
Yeah, no, that's a good way to think about it. You think of it as a drastic ROI averaging and then doing a t-test is proposing that the true pattern of effect is uniform. So it's a very strong assumption. Whereas a classifier that's happy to try to estimate a different weight for all the voxels, that's a very flexible hypothesis. And so if one approach fails, it may be because, you can think of it as it's just which one is better matched to the underlying system you're trying to figure out. Is the system more like a plateau, or is it more like some complicated forest, or I don't know what a metaphor is. So I think that's good because now it unifies the two different types of thinking about the data. They're just two ends of a continuum. Did you have something to say? Okay, what's your guys' team name? Team name. Hayes?
That's my name.
Okay, he's the spokesperson. Hayes team. All right, so
so it seems hard to imagine that you get a significant result for your classifier. You get a significant result for your univariate method, but a non-significant result for your classifier. You did your search over beta weights. somehow.
Yeah, no, it can happen. Let's take the extreme case. You have 100,000 voxels, and the true effect is the entire brain cares about, like shows a positive response to one another, but then you run your classifier, you didn't know that, and you try to fit 100,000 weights with 10 trials, and then it gets confused by the noise, and it doesn't pass your statistical threshold. Do you buy it, or we can do the simulation to
Yeah,
show?
that's fair. So if you're highly on the constraint metadata,
Right.
then you could get into a situation because you're just fitting noise.
Yeah. Cool. All right. So moving on. I guess a few more soapbox comments on MVPA. So now we're in the position to kind of think about, which we've already done a little bit of. I think that's good. You know, how is this different from or the same from subtraction? Like, what's really going on? I guess my tendency is to be a skeptic. So in the field, people are like, "Oh wow, MVPA is so cool and different and whatever." And you know, it is different, but let's clarify what they are and clarify the similarities too. So one observation is, this came up already. It's not like doing t-tests can't find like fine scale patterns. You can. I mean, you don't get those if you smooth the data, which you don't have to do. You can do high-res Fmri. You could just take it as is and do t-tests. And in fact, the floc face val t-val file, faces t-val file that we were looking at, that's what that was. Like I did it. I did a t-test at every vertex or every voxel. And those were fine scale patterns. Or I mean, FFA has a certain size, fine, and maybe it's a thing, but like it wasn't some really blurry thing. It was this pattern on the brain that we can stare at. That's one point, that fine scale activity is not the domain of MVPA necessarily. Also, you could argue this, which I kind of alluded to, the sign of the effect is completely gone, right? If your faces drive more than houses, your percent correct might be 80. Or if the houses drove more than faces, the percent correct will be 80. And if all you think about is 80%, you have no idea what the actual effect was, which is kind of funny. Also, the multivariate is not really the domain of classification. So you can take one neuron or one voxel and do machine learning classification on it, right? So if you have two distributions, my response tends to be high for faces for one voxel, and my distribution of responses for houses over here. I can draw a hyperplane. It's a one-dimensional hyperplane, so it's a dot, it's a point. And I can try to do percent correct, and my voxel can do it. In fact, I could pick a voxel in the NSD dataset, and it'll do, if I chose the right voxel in FFA, it'll successfully classify what category was on the screen. So you can do univariate classification. There's no problem with that. And so my kind of summary of all of this is, the similarity here is they're both methods for establishing whether the manipulation, so A versus B, whatever that is, for establishing whether that is changing the bold response in whatever voxels you're analyzing, right? They're very similar in that respect. Yeah, question?
But it's hard for me to think of how for the first point, but I think your first point about fraction can also get this. I don't immediately see how you abstract away from that to do something across the group, for example. So, you know, in my 30 subjects, we see that this group, even with the classification, right, you can do the classification accuracy, and you're right that that's obviously well abstracted from the data, but now to get something with subtraction, if there's fine scale activity that you don't have just a blob of positive activity, it's just some fine scale activity, then in order to do something across the group, you're going to have to smooth, or you're going to have to somehow summarize that, subtract that fine grain activity.
Right. No, I agree 100%. So there are different tactics we can take. You could say this is a registration problem, and that has its own can of worms. Or you could do RSA, which is what we're going to talk about next. Or you can reconceptualize what it is about this brain region that you're measuring. So let's take ocular dominance columns. They're fine scale. Mine don't match yours. In fact, we could try to morph my columns to yours, but I don't think anyone's tried to do that. Or why would we do that? Or we can just change the game and say, like, well, I found them. I have 100 of them. They're 1 millimeter thick. They have preference level of 50%, and you have 2 millimeter thick ones, and they have a preference level of 0.3, and like summarize at that level, right? Yep.
Comment that I think you're trying to compare MBPA and subtraction here. And to me, it seems to be that I would compare MBPA multivariate analysis with univariate analysis, and subtraction and classification. It seems to be so yeah, you see subtraction can reveal fine scale activation. So let's say if you look at the individual voxels in the FFA, for example, yeah, then you can also see the fine scale differences using classification or using subtraction. But for subtraction, usually people use it in the univariate approach because they take the responses of the whole FFA. That's one of the main activations in the FFA for faces compared to houses, for example. And I can do classification. So yeah, so the
I see.
is more about
I see. So there's a 2 by 2 again. So there's subtraction, MBPA, and there's I guess there's one element of that table that no one really does, which is univariate classification. Someone should do that. Just, yeah, you could do it.
Sorry, just one thing to add to this, right? It's you're also considering mostly your 2-class classification.
Yeah.
But if you have multi-class classification, then that would be something that's hard to summarize as much with subtraction.
Yep.
So those are something that's harder to summarize.
Yep, that's true. Yeah. Cool. We weren't even in a breakout session. Yeah, stuff happened. Okay, so one last thing on MBPA. This really is a precursor to talking about encoding models, I guess. So let me kind of walk you through this figure. It kind of makes a basic point, but there's a lot of stuff in the figures. So, and this is just from a review opinion paper that we wrote. Okay, so in this little schematic, we got our multi-voxel activity pattern, some like selection of voxels over there. And so this is a cartoon example, and we're just going to draw our hyperplane since we love to do that. And so what we're looking at here is some quasi data. Suppose we did this, and we have strength of voxels 1's response, strength of voxel 2's response. This is just 2-dimensional. Of course, you can scale it to 100-dimensional. And then each letter is just some hypothetical data point. So I measured the response to a clip of a romantic comedy movie. I do a couple different clips, great. Then I also measure the response during an action movie. And it just so happens that the activity lands here. And then I train my classifier, and it essentially estimates what the optimal hyperplane is to separate, figure out was given a pattern of activity, does it fall on which side of the hyperplane, and then that's its prediction, right? So standard setup. And so let's say we did this, and then we're happy because that looks like a 80% correct scheme. And kind of the issue we talked about, or one of the issues we talked about in this paper is that's fine, but to make the claim that the genre of the movie is somehow the thing that this area cares about, I mean, that's a step beyond what this shows, because there are alternatives, right? It could be, and we just schematically show that here. These are like histograms. You take the stimulus clips and just quantify a couple properties of these stimuli. So like the visual energy. So action movies are going to have a lot of motion and whatever. So it might be that the clips you chose under the action category will have a dramatically enhanced visual energy quantification, whatever doesn't matter what the quantification is for this example. And then your romantic comedy clips are slow and non-moving, right? So it could be that, it's not the genre, it's like the visual energy, or choose your favorite property, right? And so I think that the subtle point here is it's hard to kind of formulate kind of model selection or feature choice in kind of the classification framework. And so we talk about in the paper, well, why not just pose those hypotheses? And we'll get more into this on the next lecture, and kind of decide which of the various models actually is best explaining the activity you observe from each voxel. Anyway, so I mean, this actually applies to subtraction also, right? If just by observing higher activity in one thing than another, there are many possibilities why that is, right? And so it's really a question of experimental design or kind of background neuroscience theory as to, do you strongly believe it's the genre, or have you ruled out these other things? And so this is a general issue that affects not only MVPA, but also like a naive subtraction approach. Okay, so in summary, to kind of tie this all together, my one phrase summary of MVPA is determine whether the bold response, and then implied it's actually just several voxels that we're talking about at a time, is reliably different. So reliably is meant to imply you did it on a test set and it actually reproduces or generalizes to new data. Is it reliably different across the experimental conditions you're interested in? Again, A and B, phases analysis. So if you pitch it at that level, it sounds very suspiciously similar to subtraction. And maybe that was my intention here. Of course, there's the statistical power issue, which is good. So that's one difference. And in terms of implementing this in code, it may be more difficult. That's kind of a meta issue. It's not about the approach. It's just it's practically a little more tricky to implement correctly, say. And the interpretation issues are a little, the weight. Can you actually interpret the weights of the voxels? And if you're trying to do this on many voxels, you're going to do regularization, and that comes with its own interpretation difficulties and so on. So that's at least my take on how to maybe think about this in comparison to a bread and butter subtraction approach. This Hoffa paper talks about try and interpret the weights in a classifier, so you can see that. I don't know what the year is, it's hidden. 2014. And this Etzel paper talks about also weight issues. So it's like you determine high percent correct in the searchlight, but the gist of that article is there could be many voxels inside that searchlight that have nothing to do with, right? So just because the searchlight worked doesn't mean that all the voxels in the searchlight actually contribute, which is kind of obvious, but maybe this goes, it's worth stating if people don't realize this. Okay, so that's MVPA, and maybe we'll spend a few minutes. I don't know if there's more thoughts on MVPA, but 3 minutes just to see if there's any further discussion. We're coming back together. Shh.
You were kind of talking about how to interpret the percent correct result for the decoding. Like if you found an area that has really high percent accuracy result, like what does that even mean? Can you say that area is necessarily?
Well, it means this. I don't know what this means, but it means, so if these clouds are far apart, it means that region responds highly differently.
So like if you have lots of different region interests and you're trying to decode one particular property of the stimuli, and you can decode really, really well in V1, but if it's like motion stuff and you want it, you're expecting to see a high accuracy result, decoding result for the MT, but in V1 the result decoding much higher than this. Like you can't, it's hard to interpret it just by looking at this.
But no, I know what you're getting at, but V1 can care about motion. Like, why is that a problem?
They care about motion, but just in there are different regions of interest, and just because it has high accuracy, decoding rate, you can't necessarily say that it cares about that most.
I'm not quite getting.
Just because there are accuracy differences between regions, right? I mean, first of all, it's just the number of voxels will be important. Will influence that potentially a lot.
Right.
It's very hard to compare accuracy.
Yeah, and also noise level. So if V1 was closer to the coil, it's privileged because it is closer to the outside of your brain. So yeah, it's not easy. By the way, that's another argument for effect size, right? Noise level, that you want a quantification that theoretically is invariant to the noise level. Anyway, sorry, what?
I'm just going to, if you're trying to say like where is most relevant for motion, because you can't answer that question just by looking at accuracy.
It's a tricky situation. My view is like you did answer it, right? If you use all your voxels in V1 and you set it up in this framework and it got higher % correct, that is the answer. But it's maybe for some reason not the answer you wanted, right?
I agree with that. Right? So classification is just a tool. So you have data and you have two conditions, two sets of things, and you want two labels, and then you have classification. Successful, it could mean something that your hypothesis tries to test, or it could mean that it's something else. The core one, it's just a tool that you can use to see whether you can successfully separate two sets of data.
Yeah. So let's link that with this effect size thing. So what the data told you was V11. It was 95%. But you can pose this as like, well, was it a simple RF coil issue? So then you have to do additional analyses to control for that. So sorry, RF coil, right? If you're closer to the MR signal is detected in the coils and they have a drop off in sensitivity. If you put the coil near the brain region V1, it's gonna have better data. The TSNR will be higher, things like that. So you get 99% in V1, you get 80% in MT. You could say, well, is this a simple artifact of V1 happens to be closer to your coil? And then you can do analyses that answer that question. And then I think the road will eventually lead you back to univariate analysis. But that's a separate discussion. What was your team name? You can't use someone's name. It's got to be a thing. Brady Bunch. Is one of your names Brady?
Brainy.
Brainy Bunch. Yeah, you guys all wear glasses. Any group want to talk about, or were you sick of MVPA? I see sickness. Okay. So moving on. So the last one in this little lecture one, and then we'll do an extended break, is RSA. So in one sentence, I would characterize this as create a matrix, a 2D matrix rather, that quantifies the dissimilarity of activity patterns for different experimental conditions. And there's a subtlety here. I use the term different because typically you do this with more than two things. So far we were like A versus B, A versus B, A versus B. Here, RSA, I mean, you could do it with two, but it's kind of trivial. So it kind of implies you have many conditions. And hence the word different, not just two. All right, so let's unpack this a little further. So we set up our little matrix. So X is a bunch of voxels, 100 voxels or 10 or 1,000. And then you have different experimental conditions. So let's imagine you have 10. Faces, places, body, tools, checkerboards, people, whatever. Right, so we have 100 voxels by 10 conditions. Right? And these, let's say, are beta weights. Just make it easy, not time series. So these are just measurements of activity from Fmri or EEG, whatever. It can be whatever you want. And then all we're going to do is create a conditions by conditions matrix where element ij, so row I, column j, is just 1 minus the correlate. I'll talk about that in a second. But essentially, you look at columns I and j, which are just activity patterns. So the response to faces, 100 voxels, the response to places, the same 100 voxels. And you quantify the correlation. So, and I mean, there's a typical measure, 1 minus the correlation. So let's think about what that means. In FLOC, there's baby faces and adult faces. So let's just imagine the response is identical, up to noise. So the correlation between the baby column and the adult faces column is 0.98. And then you do 1 minus 0.98, you get 0.02. So it's very small. So this is a dissimilarity measure. So it's very low dissimilarity. All these double negatives. Okay, so these two columns are very similar. So all that means is this brain region responded to these two conditions very similarly. It like doesn't care about the fact that one was a baby and one was an adult. It's like face, age invariant face response. right? Okay, so 1 minus correlation is a common dissimilarity metric. And we do that for the ith and j columns and all of them. So adult faces, baby faces, and all the other categories. And then we end up with a conditions by conditions matrix, a 10 by 10 matrix of values where these values are dissimilarities. All right, so let's look at an example. Sorry, the example will be on the next page. Okay, so hopefully that's clear in the abstract, and then we'll actually see figures. It's good to understand it at both levels. And there's immediately something we can say about this to link it to the other approaches. This is really just MVPA on steroids. So let me let that sink in for, and then I'll try to explain it. So think about the cloud plot. You're in voxel state space, and you have faces, adult faces here, and baby faces basically occupy the same part of the cloud. So you can't classify them as different. It'll be like 50% correct. But let's say you had faces and insects. Insects that don't have faces, like fruit flies. Actually, they probably have faces if you zoom in. So let's say, but if you view fruit flies at normal viewing distance, they don't look like they have faces. So anyway, you have the fruit fly category. They're going to be miles apart in that state space. So classification will be 99%, right? But that's equivalent to saying they're very dissimilar. So if you were to quantify it this way, you correlate the fruit fly column with the adult face column, and the correlation will be very small, 0. And then 1 minus 0 is 1. So that's a very high dissimilarity, right? So separability of the clouds in kind of a hyperplane setting is equivalent to high dissimilarity. So making this matrix is really just putting MVPA results, classifier results, but the units are different, but let's ignore that for a second, into a 2D matrix, right? It's just taking MVPA to the next level for many conditions. So why is this useful? Well, this is maybe my opinion on this. It's useful if you want to think of this as a way to just summarize a lot of data or look at it quickly. It's useful. It's a way to summarize complicated thousands of voxels into a single small matrix. Going along with that, you can think of it as compression and summary. And then primarily it's been proposed by Nico as a way to, as an approach, an analysis approach to start putting different types of data on the same footing. So like EEG and MEG and Fmri and a computational model and behavioral, all this stuff. You can kind of construct this matrix based on different measurements, and then you can compare, right? So that's the conceptual level. Let's look at a simple example. I took this slide from Jan. Jan is actually a collaborator on the NSD data. So this is his slide, or actually it's probably Nico's slide, I don't know. Okay, so we have various stimuli that we design for our neuroscience purposes, and then we get this pattern of activity, this in a nice pretty picture here, and then we get one other condition, say, and we get some pattern, and they're going to be different depending on what area we choose. And then we measure dissimilarity somehow. Let's not worry about exactly how. And then we just fill in this small matrix, actually. It's a 6 by 6 matrix, and this is the umbrella hand dissimilarity, and it's dark red, which means fairly similar. Sorry, this is the color bar for this. So dark red is very dissimilar. Okay, but doesn't matter. So you fill in this matrix from your ROI or your searchlight, whatever you want to call it. And then that is a representation of the data, but it has lost information, right? You could have 1,000 by 6, but now it's just 6 by 6. Okay? So that is the data in a sense, or it's a transformation of the data rather. And then what we can do is now construct the similar idea from other things. Here it's a pixel-based dissimilarity. So that just means take the image itself and look at the pixel intensity and essentially construct this matrix. So it's now, you have pixels by 6, and then you do this kind of dissimilarity. You know, that's just one example. You could also do it from a more sophisticated image processing model or something like that, or you can do it based on some behavioral. So ask people, is that similar to that? And I would say that's pretty different. So that would be highly dissimilar. Anyway, so you can repeat this process. And then you can start comparing these things and trying to understand, is the brain most like behavior? Is the brain most like pixels or whatever? So that's basic setup. That was toy data, but we can look at what real data might look like. Again, coming from Jan. So this is ventral cortex. He selected a little ROI mask from a subject, just as an example. And then these were the stimuli he used. There are many. And the details don't matter too much, but I mean, you get something that looks structured, and it looks structured because the stimuli were ordered judiciously. And so you can kind of highlight something happening here. So the faces happen to be these images, and they were grouped here, and you can see it's pretty blue, and if you look at the color map, it's pretty lowly dissimilar, meaning very similar. The response to these various stimuli were highly similar in this region of interest, right? So it kind of provides some visual evidence, proof by eyeball, that in this part of the brain, ventral cortex, these stimuli are kind of treated very similarly. And then, and so on. Okay, breakout on the idea of RSA, and yeah, so let's spend 5 minutes on that. Reconvene. Group in the back. Wait, are you part of one gigantic group? Yeah, what's your group name? What? SFP. What does that stand for? Whoa, what? I missed it. What? Is that a thing? Yeah, you guys have thoughts on RSA then?
Yeah,
so we're talking about what if you're like in theoretical, if you have this, you can just have high correlation, but actually you can find high correlations using this method. Maybe like we think about some detailed things like how do you choose the data points for each voxel for each condition? Is this average for the whole trial or block, or you just choose the point? But if you don't find a high correlation between the two very similar conditions, how can you use this?
You raised one issue earlier, which was like the units that you compute on. So the time point or the beta weight or the whatever, yeah, that's a important choice. It's a bit out of scope, right? It's a separate issue. But the second issue is what happens when you don't get something that fits your expectation. I mean, it's important, so I would just class that as if your data are extremely noisy, the correlations will tend towards 0, and then everything, you won't find any structure, which is actually a hard and deep issue. I don't have a short answer for that. I don't know if people have thoughts.
You can assume that the data is super good and that somehow the faces just don't have any correlation.
Like the activity elicited by the faces have not correlated. So yeah, so that might be a good thing. Maybe the area doesn't represent what you think it represents. Or yeah, it's not a bug. It might be a good thing.
Would it also perhaps inform you of the quality of what you've chosen for the features and your representations? Because presumably you have to have a choice of what features you're actually comparing.
Hold on. So in the data matrix, well, what I'm calling the data, there's no selection of feature. You're just using the voxels to, right? You're computing similarity based on whatever the bold activity was. So there's no choice of feature, right? So actually, actually on the noise issue, so one useful trick you might consider doing, and people do it and it's not crazy, and actually dates back to like Haxby land of like split your data do. But anyway, so the point is, how do you know if your data are good or not? And if noise is corrupting everything? Well, if you repeat the trial, like the exact same stimulus or exact same whatever, you can do a, for example, split half RDM. So the rows come from the 6 conditions, but from half the data. And the columns come from the same 6 conditions, repeated to the extent possible, humanly possible, given your experiment. And then you compute the dissimilarity between the even 6 categories and the odd 6 categories. And if the diagonal is crap, then you know your data is crap, right? The diagonal should be replicable. You just essentially repeated the trial, and it should be reasonably high. And if it doesn't look high, then you should get better data. Oh, cool. Yeah, oh, more comments from SFP. Oh, RDM, yeah, sorry, did I? Representational dissimilarity matrix.
Thank you.
Yep.
Sorry, trying to compare with the ambiguity.
Mm-hmm.
If we use ambiguity to classify multiple conditions, more than 3, it will be the same as this.
Kind of at the conceptual level. Whether it'll be numerically the same, no. But yeah, you could do, let's say you have 3 categories and you do 3 two-way classifiers to fill in the triangle. That's kind of like this.
It doesn't work if you use multi-class classification. It's always has to be pairwise classification for all possible pairs.
You can do following classification and chance levels from 5%.
No, but then it doesn't equate to this.
Yeah, no. And I think for us, actually, the strength is you can try to, so classification, you can't really understand why you get the results, right? You just know whether your accuracy is good or not, right? But I would say one strength is that in this size here too, you can construct the model and describe the relationship conditions. So you can, it can all just be similar descriptions, it could be something about the behavior. Then you can construct using this environment, product idea for different hypotheses that you have, and then you can correlate that with the framework that you mentioned. And that is, I think, the strength of this. Your experimental design allows you to.
Any other comment, discussion? Arrows? They're, oh, I think it's just meant to imply like more, this is actually correlations of correlations, but yeah, this arrow is, these are highly similar, maybe. Yeah, or people have done that, correlating these elements with these elements. And maybe this is just supposed to convey, oh, that's a really strong correlation. Let's talk about that after, that's the next section, and then we'll do a real break. That's a nice segue. So yeah, multidimensional scaling comes, it's very intimately tied to it. So let me just remind people what that is.